In this session, we'll be having a look at higher order differential equations, that's third, fourth order, etc., using what we've found already from first and second orders, and then looking at linear systems. So, a homogeneous linear ordinary differential equation with constant coefficients of order n can be written as this differential equation here, and so we can establish one of these with constant coefficients of order n starting with our nth derivative, and so we're looking at any order. Notice the coefficient terms in terms of a are all constants. So as we did with the second order, we solve one of these using our characteristic equation, and remember, for these types of equations, your basis of your solution is going to be y equals e to the lambda x, and this still applies even when we have an nth order equation. So we set up a characteristic equation of nth order in exactly the same way as we did before, with the power of the lambda matching the order of the derivative. So, in terms of what sort of answers we get out of it, well, in terms of if we have the distinct real roots, we end up with our exponential functions, e to the lambda 1x, e to the lambda 2x, etc. And so we can actually solve an nth order differential equation in exactly the same way. The problem being here is, how do we actually solve this characteristic equation, because that becomes a much more difficult problem the higher the order that we get. If the roots of the characteristic equation then are all distinct but some are complex, then these solutions will be of the similar form that we had before, with our e to the alpha x times cos beta x plus sine beta x. If we have repeated roots, as we did before, we would multiply by a factor of x. So in the case of a cubic equation, where perhaps we have a repeated root 3 times, our solutions would be e to the lambda x, x e to the lambda x, and another repeat by multiplying by x again to give x squared e to the lambda x. For multiple complex roots, the real solutions are similarly obtained. In other words, if we have a double complex conjugate root, alpha plus or minus I beta, we would have e to the alpha x cos beta x, e to the alpha x sine beta x, and if it's a repeat, we multiply by x, and so end up with x e to the alpha x cos beta x, and then x e to the alpha x sine beta x. So just let's have a look at some examples of these. So first example, solve the differential equation y triple dash minus 6y double dash plus 11y dash minus 6y equals 0. This leads us to this cubic equation. Lambda cubed minus 6 lambda squared plus 11 lambda minus 6 equals 0. So how do we solve one of these? The first thing to realise is we look at that number on the end and find out what are the factors. So the factors of 6, 1, 2, 3, and we can perhaps not think about 6 because then that would not give us a cubic. So one thing we can do by trial and error is to try some of these, and these could be plus or minus. So we may have to try a few things, but let's just try. If lambda equals 1, substituting the characteristic equation, we see we end up with the answer of 0. So we know that's a solution. Try lambda equals 2, and we also end up with 0 as a solution. So that one's also a solution. And lambda equals 3, and we see that one. So by trial and error sometimes, we could work out what the factors are. And so in this case, lambda equals 1, 2, and 3. 3 distinct real roots, so we get e to the c1 e to the x, c2 e to the 2x, and c3 e to the 3x as a solution. So let's consider the next example. Y, and notice here the notation we're using, we don't use 4 dashes in our prime notation, but the number in a bracket signifies derivative. So this is the fourth derivative minus 16 times y. So the characteristic equation will be lambda to the power 4 minus 16. And we can consider this as being lambda squared all squared minus 4 all squared equals 0. So we have a difference of 2 squares. So it becomes lambda squared minus 4 times lambda squared plus 4. And we can factorise that into lambda minus 2, lambda plus 2, lambda minus 2i and lambda plus 2i, and so end up with our 4 roots. So remember, if you start with a fourth order equation, you must have 4 roots. So we have c1 e to the minus 2x, c2 e to the 2x, c3 cos 2x, and c4 sin 2x. So looking at this next example, it's a fourth order equation, so we're going to expect 4 roots or solutions out of this equation. Setting up our characteristic equation, and in the same way as we did before, look at the factors of 16. So we've got 1, 2, 4, and 8. And by trial and error, we only find out that lambda equals minus 2 is a root of this equation. So what does that mean is that the others aren't whole number roots, like the factors of that term. So that means they're either repeated roots or complex roots. And so what we've got to do is find out some way of solving this fourth order equation. One way you could do it is by long division and say we've got lambda plus 2 out the front of lambda to the power 4 plus 8 lambda cubed plus 24 lambda squared plus 32 lambda plus 16, and carry out your long division. Now that can get a bit messy, but as we'll see, there is a simpler way that we can do this. So the simpler way we can do this is called synthetic division. So what we set up is that out the front we have that root that we know, and then we write down all the coefficient terms. So that was 1, 8, 24, 32, 16. So then we write down that 1. And so the process is we say minus 2 times 1 is going to give us minus 2. And then we add those two terms together to give us 6. Then repeat it. Minus 2 times 6 is minus 12. 24 plus minus 12 is 12. Then minus 2 times 12 is minus 24. And that leaves us 8. And then minus 2 times 8 is minus 16. Add them together and we get 0. We want a 0 here because that's our remainder. And then we read our answer this way. So it's 8 units, 12 times lambda plus 6 lambda squared plus lambda cubed. And so notice what we're doing. We've reduced it by a power of 1. We now have a cubic, and we can repeat that process again. So write down your coefficients, 1, 6, 12, 8. And the answer that we know is minus 2. Because we can check then, in this case, check here. The factors would be 1, 2, and 4. And if we let lambda equals minus 2, we find out that it is actually a root for it. So that's where that minus 2 has come from. So write down the 1. So minus 2 times 1 gives you minus 2. 6 minus 2 is 4. Minus 2 times 4 is minus 8. 12 minus 8 is 4. Minus 2 times 4 is minus 8, and that's 0. So that's our remainder. And so we've got 4 plus 4 lambda plus lambda squared here. And we know that lambda squared plus 4 lambda plus 4 factorises into lambda plus 2 times lambda. So we have lambda equals minus 2, a repeated root, and it's repeated 4 times. So we've got e to the minus 2x, x e to the minus 2x, x squared e to the minus 2x, and x cubed e to the minus 2x. So, as with the constant coefficients ones, we can also then establish patterns for solving our higher order Euler-Cauchys. These just become a little bit more involved, but you see the same pattern is for an Euler-Cauchy, a third order. The power of the x will match the order of the derivative in each case. So that's how we identify our Euler-Cauchy equation. So as we saw before, our basis of solution is our y equals x to the m. And if we substitute that into the differential equation, this time round we'll end up with this for our auxiliary equation. So m minus 1, m minus 2 plus a2 times m by n minus 1 plus a1 times m plus a0 equals 0. We could also establish a similar pattern for our fourth order Euler-Cauchy. Notice this time round, our first term becomes, we're adding in. So let's consider this third order Euler-Cauchy, checking that the power of x matches the order of the derivative. It's a cubic equation, so we're going to expect 3 solutions. Setting up your auxiliary equation leads us to the cubic equation m cubed plus m squared minus 7m minus 15 equals 0. So by trial and error, as we did before, we could show that m equals 3 is a root of this equation. And so to find the other solutions, using our synthetic division, put the 3 out the front, then our coefficient terms are 1, 1, minus 7 and minus 15. So write down the 1. 3 times 1 is 3. 1 plus 3 is 4. 3 times 4 is 12. Minus 7 plus 12 is minus 5. 3 times minus 5 is that should be a plus 5. So that's plus 15. To add them together to give us that remainder of 0. So our solution then will be, I'll just take that out. So we get then that m cubed plus m squared minus 7m minus 15 is m minus 3 times m squared plus 4m plus 5. So to solve this then, we would use our quadratic equation, our quadratic formula, and that gives us that we have conjugate complex roots. Now notice here, if it's going to be a complex root, it will always appear as a conjugate pair. So we have 1 real and 2 complex roots. So our answer will be c1x cubed plus c2x to the minus 2 times cos ln x plus c3 sin ln x, in the same way as we did before for complex roots of an Euler-Cauchy equation. Now let's consider the higher order non-homogeneous equations. And as we found before, we have a general solution of our homogeneous plus our particular solution. And in finding that particular solution, we had the method of undetermined coefficients or the method of the variation of parameters. Now, your undetermined coefficients can be applied in exactly the same way. There's no restriction on the order there. However, for variation of parameters, we're going to have to extend our method to now our nth order, and we'll look at that shortly. First of all, consider the example where we have constant coefficients and it's a non-homogeneous case. So we have constant coefficients, non-homogeneous, so we have to look at finding our homogeneous solution to start with. So setting up our characteristic equation, and notice this is one that we solved in a previous example. So in the same way as we've done before, we identify what the roots are and we find out we have lambda equals 1, 2 and 3. So our homogeneous solution will be c1 e to the 2x, c2 e to the 2x and c3 e to the 3x. Now considering the function on the right hand side, it's a simple exponential, and so I can use the method of undetermined coefficients and have yp equals some constant times e to the minus x. So calculate your first derivative, second derivative, third derivative, substitute it into the pattern of the differential equation, identify your coefficients, and we end up with a is minus 1 on 12, and so our particular solution yp equals minus 1 on 12 e to the minus x. And so remember our complete solution then is our homogeneous plus our particular solution. So non-homogeneous, higher order with constant coefficients, fairly simple in this particular case to just apply the method that we've done previously. So now we want to have a look at our method of variation of parameters. And as I said, we need to establish a formula that applies to an nth order equation. And so this is the formula here. We're not going to establish this formula in terms of proving where it comes from, but notice it's got a similar pattern to we used before. y1 times some integral plus y2 times another integral, and so forth and so forth. So look at this term that we have here in the integral. We've got the Rx and Wx that we had before, and remember your W is your Wronskian standing for this determinant, where your homogeneous solutions go in the first line, and then we find our derivatives to complete the determinant. So what about this W1, W2, and etc.? So looking at the W1, 2, 3, etc., it says it's obtained from W by replacing the jth column of W with the column 0, 0, 0, 1. So we've written it in that transpose notation to save room. So W1, for example, we put all zeros except the last element in the first column being 1, and then the other columns are the same. So similarly for W2, our first column would be W1, Y-1, etc., down to Y-n minus 1, 1. And then your second column would be 0, 0, down to 1. And then your other columns would be the same as previously. Now, just checking, does this work for when we just had our normal 2 by 2 case? So if n equals 2, your Wronskian would be y1, y2 followed by its derivatives. So W1, replace the first column with 0, 1, and your second column is the same. So when you work out your determinant, you get minus y2. And W2, replace the second column, work out your determinant, and you end up with y1. And so we end up with the formula that we had for our second order case. And so you could remember or work it out just using that nth order formula. So let's just have a look at an example of one of these, and this is here for information rather than examinable content, because it gets rather messy, because you see here we have to work out in this case to get our final answer 4 3 by 3 determinants. But let's go back to the beginning. So we've got a third order, it's constant coefficients on the right, but in this case it's got e to the x divided by x, which we know we can't do unless we use variation of parameters. So our homogeneous case, looking at our characteristic equation, lambda cubed minus 3 lambda squared plus 3 lambda minus 1 equals 0. And using some of the techniques we've investigated, we could discover that that's actually a cubic, and we have lambda equals 1 repeated. And it's always helpful, I find, to write it down to remind you that we have 3 solutions because it was a third order equation. So we have e to the x e to the x, and x squared e to the x as our 3 solutions in our homogeneous solution. So they become our y1 and our y2, setting up our w, y1, y2, y3 in the first line, working out their derivatives, and this just becomes messier because we're using our product rule, and we evaluate out that determinant. So then we find out our W1, replace 0, 0, 1 in the first column, the other column's the same, evaluate out the determinant. For W2, put 0, 0, 1 in the second column, work out your determinant, and then for W3, 0, 0, 1 in the third column. And note here, our r of x is e to the x on x in this particular case. So we then have a look at our yp, then would be y1 times w1 r over w, y2, w2 r on w, and then y3, w3 r over w. And working out those integrals, you see that e to the 2x times e to the x and the e to the 3x cancel out. So the first integral becomes the integral of x over 2. This integral, the e to the x's all cancel out, the x will cancel out, and you get the integral of minus 1. And in this case, we end up with the integral of 1 over 2 x. And so our particular solution becomes minus 3 on 4 x squared e to the x plus a half x squared e to the x. Writing out our solution as our homogeneous plus our particular solution. But just note this time round, as sometimes can occur, we have that term which is c3x squared e to the x minus 3 on 4 x squared e to the x. They can be combined together in just a constant times, but you could just leave the answer like that. So using variation parameters does become a little bit longer the higher order that you get. So, what's an application of a fourth order differential equation? Just again for your information, not as an examinable thing, is that an important application of a fourth order differential equation is in the study of the bending of an elastic beam, such as a wooden or iron girder in a building or a bridge. So for some of you, this may be an important calculation. So, consider a beam B of length L with a constant cross-section and made of a homogeneous elastic material, for example steel or something. We assume that under its own weight the beam is practically straight. If we apply a load to the beam in a vertical plane through the axis of symmetry, usually taken as the x-axis as the diagram shows, the beam will bend. Its axis will be curved into the elastic curve or deflection curve C, as shown in the diagrams. So if we assume that the bending is small so that the deflection y of x and its derivative y dash are also small, it can be shown using elasticity theory that mx equals ei times y double dash x, where mx equals the bending moment, E is Young's modulus of elasticity, and I equals the moment of inertia of the cross-section about the horizontal axis. Elasticity theory further shows that m double dash equals fx, where fx equals the load per unit length. And so we can obtain this equation here, which says ei times y4, i.e. the fourth derivative, equals f of x. So here's a fourth order differential equation where E and I are just constants. So in order to solve one of these things, we need to consider some important boundary conditions. So in terms of this beam, depending on the support of the beam, there are three important sets of boundary conditions. If it's simply supported, i.e. not clamped or anything, just simply resting on two supports at either end of the beam. So at these, your y and y double dash is 0 at both ends. If it's clamped at both ends, we get a second set of conditions so that y equals y dash equals 0 at both ends. And if it's clamped at one end and free at the other, we get this set of initial conditions. So let's consider an example of these and see how we can end up with a solution. So find the deflection in an elastic, simply supported beam where the load Fx is a constant F0. We have this differential equation here. So Ei times y to the fourth derivative equals F0. Ei and F0 are all constant, so just call it K. So K equals F0 over Ei. So this is a simple fourth order equation, but to solve our third derivative we just integrate both sides, and to solve our second derivative we again integrate both sides. So we end up with this equation here where we substitute in, so notice it said it was simply supported, so simply supported at both ends, y double dash and x equals 0, so that gives us C2 is 0 and y dash is 0 at L. So we're going to end up with C1 being a constant related to the length of the beam. And so we end up with this equation here. The next step then is to integrate that equation twice to end up with y equals this term here. We then substitute in our boundary conditions again to help us evaluate out those constants, and so we can end up with this expression here, gives us the deflection of a beam as a function of the distance from the endpoint. If we then go back to what k was equal to, f naught over ei, we're going to end up with this equation here for our beam deflection. And a graph of that is just shown in this diagram here. So I said this is just put in here. It's a very simple case of a fourth order beam, fourth order equation to give us that equation for the deflection of a beam. The last thing we're going to look at in terms of these differential equations are these things called systems of differential equations. Systems of ODEs can be used to model complex phenomena with interacting subsystems, such as the interaction of species or multiple connected brine tanks, mass spring systems, circuits, etc. They can also be used as an alternate way of expressing higher order ODEs. In the following, t will now be used as the independent variable. That's purely because these things are usually time related. So, what does a general system look like? So in a system of equations, you have a set of equations operating at the same time. So here we have a set of differential equations operating at the same time, and we're only considering a first order system. So it's a system of first order differential equations. They can be homogeneous or not homogeneous. So if it's homogeneous, those functions on the end won't exist. So we can write this homogeneous system in form of, we have a system of derivatives equals some constant times our y terms and perhaps some other function. So in terms of matrices, our y is our functions y1 down to yn. A is our matrix of the coefficients of those terms, and so in this case we only will be considering those that have constant coefficients. So, a first order system with constant coefficients will have a solution of the form, so it's got constant coefficients, so here we would expect that exponential function in our answer. And so we'll get some constant, in this case the constant will be a matrix. So we've got y dash equals ay, so if our solution is x e to the lambda x, we're going to get, differentiating that, we'll have lambda x e to the lambda x equals ax e to the lambda x. So taking, if this is our solution, if I differentiate that, I get lambda x e to the lambda x equals ax. So if we take out the lambda x's, we end up with this equation, lambda x equals ax. And if you remember, that equation was where we looked at solving this in terms of our eigenvalues and eigenvectors. If you remember back to Maths 1, that was the equation that we had in finding our eigenvalues and eigenvectors. So to solve one of these first order systems, we are going to use our eigenvalues and eigenvectors. So if we have this first order system here, given as this set of equations, our matrix of coefficients is A, and that was 1 minus 4 minus 2, 3. So finding our eigenvalues, setting up our determinant, we find our eigenvalues of minus 1 and 5. Remember then, you take each of those eigenvalues, substitute it into the matrix, form our augmented matrix, reduce it, work out our combination of our coefficients, and in this case the two coefficients are the same size but with opposite signs, so we can say our eigenvector would be minus 1, 1. We then take our other eigenvector, minus 1, and in the same way we can establish its eigenvector is 2, 1. So the solution will be of the form eigenvector times e to the eigenvalue, and so it's c1 minus 1, 1 times e to the 5t plus c2, 2, 1 e to the minus t. And if we expand that out, we could get it written in terms of our system as minus c1 e to the 5t plus c2, 2e to the minus t, and then c1 e to the 5t plus c2 e to the minus t. So some applications of these, and these are, if you want to see the expanded form of these and then worked out fully, have a look at the notes, but they're put there just for your information. And so where we can end up with a system is if we have a mixing problem with two tanks, like one tank, so we have our mixing problem where we have our tank, something coming in and something going out. But in this case, it then runs into a second tank and runs out of that. So to solve a system like this, we set up a system to do it. And you can see that fully worked out in the lecture notes. The other case is where we have a network. The following electric network, find the currents, assuming that all charges and currents are 0 at t equals 0, the instant the switch is closed. And so in this particular case, again, using our RL and RC circuit formulas, we can work out our answer to this one, setting up our two systems and then using our eigenvalues and eigenvectors to find the solution. So, in terms of our general nth order case then, if we have an nth order differential equation, we can set up an equivalent system in terms of first order ODEs. And so sometimes it's easier to solve an nth order by using systems to do it. So having a look at this example, if we want to convert a third order differential equation, for example, into a system. So, step 1, we write the equation with the highest derivative as the subject. So, writing them in terms of a1y plus a2y dash plus a3y double dash, etc. Now, this is a third order system, so I want to define 3 new functions, and it's going to be a 3 by 3 system. So I'm going to define y1 as being equal to y, y2 as being equal to y dash, and then y3 being equal to y double dash. We then differentiate these equations to establish that y dash 1 is equal to, and if I expand this out, it would say y dash 1 would be equal to y double dash, and that's equal to y2. So that's where that came from. Same way, y dash 2 would be equal to y, sorry, that's not y double dash, that's just y dash. And then y dash 2 would be y double dash, and y double dash is equal to y3. And then y dash 3 different would be equal to y triple dash, and from this equation here, substituting this, that becomes ay1 plus ay2 plus ay3. So your coefficient terms would be 0, 1, 0, 0, 0, 1, a1, a2 and a3 times y1. So we have our system set up. And so we could find this by finding the eigenvalues and eigenvectors of that matrix. Now, in terms of what we can do with these solutions, we need to be able to analyse these systems, and we use these terms here to analyse. So we talk about the phase plane, the critical points, and stability analysis. The phase plane. The solution to a second order linear system will be a system in terms of these two functions y1 and y2. And both y1 and y2 are functions of time. And so we could plot these two curves, y1 against time and y2 against time, but that doesn't tell us how y1 and y2 interact with each other. If we could take the two equations for y1 and y2 and eliminate out the t, we could also plot these as a single curve on the y1, y2 plane, and this curve is called the trajectory of that system that we're trying to solve. The y1, y2 plane is called the phase plane, and if many trajectories in the y dash equals ay are plotted, we could obtain what we call a phase portrait, which gives us a description of how the system behaves. So for example, looking at this linear system here, we could show by looking, so in this case, your matrix of coefficients would be -3, 1, 1, -3. And if we went through and found the eigenvalues and eigenvectors of this system, we'd end up with the values would be -2 and -4 with their corresponding eigenvectors. And so end up with this solution here, that y1 equals c1 e to the -2t plus c2 e to the -4t. y2 is c1 e to the -2t minus c2 e to the -4t. And if we eliminate t out of these equations, we end up with a term like this, which are actually a family of parabolas. And so if we sketched for different values of the constants, we could show that this is what your phase plane would look like. And so it gives us how the system is going to behave. But in terms of being able to eliminate t from this solution equation, often is quite a difficult thing to do. So it can be difficult to determine what these solutions are. We can use computers to aid us in this and so get a good picture of what the phase plane looks like. So having a look then at your critical points for a system. So as we did in curve sketching, a critical point can determine how the curve behaves at those important points and so give us a picture of what the curve looks like. So in the same case here, the critical point is going to tell us how the system behaves without necessarily having to solve the system. So a critical point of an n equals 2 system, so a 2 by 2 system, is where both your first derivatives equal 0, which is fairly obvious. And this is going to occur in our 2 by 2 system where at the origin where y1 equals y2 equals 0. There are 5 types of critical points, so you don't have to remember these. These are given here for your information, and for those of you perhaps going into electrical, we'll look more at phase planes and critical points, etc. So these two together, we can either have a node, and notice the nodes are such that all the trajectories come into the origin along for a proper node. We can have examples of straight lines, and this example that we saw previously, parabolic pathways. The other types of nodes is we can have a saddle point, a centre, or a spiral point. So different types of critical points determined by the phase plane, by solving that system in terms of y1 and y2. And then we can talk about the stability of the critical point. So the critical point is stable if all the trajectories are sufficiently close to the critical point for all of t, and if all trajectories approach the critical point as t approaches infinity, then the system is called attractive. So you can see a saddle point here can't be stable or isn't attractive because they're not near the critical point, which is at the origin, no matter what your value of t is. The same thing for a centre. We wouldn't call a centre an attractive critical point. So how do you determine the nature of your critical point? We look at our matrix of coefficient terms, and you are given this table here. Notice these first 4 characteristics give you your type of the critical point, and the next 4 characteristics go to the stability of that critical point. And so in terms of, we're looking at the value P, Q, and delta, all determined from your matrix of coefficients. So notice, for instance, if your determinant is greater than 0 and that expression p squared minus 4q is greater than or equal to 0, we have a node. And notice then if your determinant is positive and that p value negative, that will be what we call a stable and attractive node. And so it's a case of just reading this table, and there are examples of this in your TUTE questions, and we'll have a look at some of these in the lecture workshop time.